Right now, as you settle into the comfort of your evening, somewhere in the universe exists matter so dense that a teaspoon of it would weigh as much as Mount Everest. These are strange stars, objects that shouldn't exist according to our normal understanding of physics, yet they might be scattered throughout the cosmos, hiding in plain sight among the billions of points of light in our night sky. Imagine a star the size of Manhattan, but containing more mass than our sun. Its surface gravity is so intense that if you dropped a marshmallow onto it from a height of 1 meter, the marshmallow would hit the surface at 7 million kilometers per hour and release as much energy as an atomic bomb. This isn't science fiction. It's the reality of strange quark matter, a state of matter so extreme it makes even neutron stars seem ordinary. These strange stars exist in a realm where the normal rules break down. Inside them, the very building blocks of matter, protons and neutrons, cease to exist. Instead, there's a soup of fundamental particles called quarks, freed from their usual confinement, creating a form of matter that might be more stable than anything we know. Perhaps most unsettling is this: if strange matter really is more stable than ordinary matter, then every atom in your body, every particle of Earth, every star in the sky, exists in an unstable state. We're all just waiting to transform into something stranger. Tonight, we're going to explore these impossible objects, these strange stars that challenge our understanding of matter, energy, and the very nature of existence. To understand strange stars, we must first understand the cosmic hierarchy of density, the ladder of compression that matter climbs under extreme gravity. Start with water, 1 gram per cubic centimeter. That's our baseline, the density we intuitively understand. Rock is denser, about 3 grams per cubic centimeter. Lead, one of the densest common materials, reaches 11 grams per cubic centimeter. But these are nothing compared to cosmic densities. White dwarfs, the remnants of stars like our sun, compress matter to about 1 million grams per cubic centimeter. Imagine crushing a car into a sugar cube. That's white dwarf density. Here, atoms are squeezed together, electrons stripped from their orbits, creating what physicists call degenerate matter. Neutron stars push even further, 100 trillion to 1 quadrillion grams per cubic centimeter. This is atomic nuclei touching each other, protons and electrons crushed together to form neutrons. A sugar cube of neutron star material would weigh 100 million tons. But strange stars, if they exist, go beyond even this. They represent matter compressed to its theoretical limit, where the very nature of particles changes. They exist at densities where our equations start producing infinities, where quantum mechanics and general relativity clash, where physics as we know it begins to fail. To understand strange stars, we need to dive into the world of quarks, the fundamental building blocks of matter that are normally locked away inside protons and neutrons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Normal matter contains only up and down quarks. Protons have 2 up quarks and 1 down quark. Neutrons have 2 down quarks and 1 up quark. These quarks are held together by the strong nuclear force, confined forever within their particles. Under normal conditions, quarks can never be free. Try to pull them apart, and the energy you add creates new quarks, keeping them confined. It's like trying to isolate one end of a magnet. Cut it in half, and you get 2 complete magnets, never an isolated pole. But at extreme densities, something remarkable happens. When matter is compressed beyond neutron star density, quarks can break free from their confinement. They form what physicists call quark matter, a soup of liberated quarks, swimming freely, unbound by the normal rules that govern atomic matter. Here, quote, "S where things get truly strange." When quarks are liberated at extreme densities, the high-energy environment allows heavier quarks to form. Specifically, strange quarks, heavier cousins of the up and down quarks, begin to appear. This transformation follows a beautiful symmetry principle. In the ultra-dense environment of a strange star, it becomes energetically favorable for some down quarks to convert into strange quarks. The result is strange quark matter, a roughly equal mixture of up-down and strange quarks. This strange matter has properties unlike anything else in the universe. It might be absolutely stable, more stable than iron. It could be self-bound, needing no external pressure to hold together. It might convert normal matter into strange matter on contact. It could exist at a range of densities, from nuclear to beyond. If this is true, strange stars aren't just another type of compact object. They're an entirely different state of matter, as different from neutron stars as water is from ice. How does a strange star form? The most straightforward path starts with a massive star's death. When a star more than 20 or 25 times the sun's mass exhausts its nuclear fuel, it collapses catastrophically. The outer layers explode in a supernova, while the core collapses inward. If the core is massive enough, it continues collapsing past white dwarf density, past neutron star density, into the realm of quark matter. At the moment of transition, something extraordinary happens. The neutrons, squeezed beyond their limits, dissolve into their constituent quarks. The released quarks, suddenly free, reorganize into strange quark matter. The process releases enormous energy, possibly triggering a second explosion, a quark nova that follows the initial supernova. This transformation might happen in milliseconds, or might take years. We don't know because we've never witnessed it directly, but if it occurs, the result is a strange star, an object 10 or 20 kilometers across, containing 1 or 2 solar masses of strange quark matter. There, quote, some more unsettling possibility. Neutron stars might spontaneously convert into strange stars. As neutron stars age, they cool and spin down. The reduced centrifugal force allows them to compress further. If they cross a critical density threshold, a phase transition could begin. A seed of strange matter forms in the core and spreads outward, converting the entire star in seconds. This conversion would release enormous energy, possibly 10 circumflex 53 ergs, equivalent to 100 supernova. The star would shrink suddenly, its radius decreasing by several kilometers in less than a second. Gravitational waves would ripple outward. The star's magnetic field would reorganize violently. We might have already observed such conversions without recognizing them. Some gamma-ray bursts and fast radio bursts might be neutron stars transforming into strange stars. The most exotic origin story suggests strange stars formed in the early universe, seconds after the Big Bang. In those first moments, the universe was a hot, dense soup of quarks. All quarks were free, before they became confined in protons and neutrons. As the universe expanded and cooled, most quarks combined into normal matter. But in regions of slightly higher density, strange quark matter might have formed and survived. These primordial strange stars would be ancient, as old as the universe itself. They might have masses ranging from asteroids to stars. Small ones could be dark matter candidates. Large ones might still shine, indistinguishable from normal stars except for their incredible density. Strange stars challenge our fundamental understanding of matter through what physicists call the equation of state, the relationship between pressure, density, and temperature that describes how matter behaves. For normal matter, we understand this relationship well. Compress a gas, it heats up according to predictable laws. Compress it more, it becomes liquid, then solid. Each phase follows equations we can write down and solve. But strange matter breaks these rules. Its equation of state is unknown, and possibly unknowable with current physics. We're dealing with quantum chromodynamics, QCD, the theory of the strong force, in a regime where our calculation methods fail. The equations become non-perturbative. We can't solve them by normal approximation methods. Supercomputers, running for years, can only provide rough estimates. We're mathematically blind in the very region where strange stars exist. This isn't just a technical problem. It means we can't predict the maximum mass of strange stars, their radius-mass relationship, their cooling rates, their stability conditions, their observable properties. We're trying to understand objects whose basic physics lies beyond our computational reach. The strangest aspect of strange stars is the stability paradox, first proposed by physicist Edward Witten in 1984. Witten suggested that strange quark matter might be the true ground state of matter, the most stable form matter can take. If true, this means all atomic nuclei are merely metastable, waiting to decay. Strange matter is the universe's preferred state. Normal matter exists only because of energy barriers. This is called the strange matter hypothesis, and it's either completely wrong or one of the most important insights in physics. If strange matter is stable, why hasn't everything converted? The answer might be that normal matter needs an enormous push to transform, temperatures of billions of degrees, or pressures exceeding those in neutron stars. Once formed, though, strange matter would be eternal, unable to decay back to normal matter. Inside strange stars, one of nature's fundamental rules breaks down quark confinement. Under normal conditions, quarks are confined inside hadrons, protons, and neutrons by the strong force. This confinement is absolute. Free quarks have never been observed in isolation. The energy required to separate quarks creates new quark-antiquark pairs, maintaining confinement. But in strange stars, the density is so extreme that hadrons overlap. The boundaries between protons and neutrons dissolve. Quarks from different hadrons intermingle. The entire star becomes a single gigantic hadron, or perhaps something beyond hadrons entirely. This deconfined state might have properties we can't predict. Superconductivity of color charge, the quark equivalent of electric charge, superfluidity of strange matter, quantum, coherence on stellar scales, collective quark behavior, unlike anything in normal matter. The surface of a strange star presents unique puzzles. How does quark matter, which exists only at extreme density, interface with the vacuum of space? Several possibilities exist. The bare surface model. Strange matter might be self-bound strongly enough to have a sharp surface, with quark matter on one side and vacuum on the other. The surface would emit particles through quantum effects, creating a thin atmosphere of normal matter. The crust model. A thin crust of normal matter might float on the strange matter, held up by electromagnetic forces. This crust would be incredibly thin, perhaps meters or less, but could support normal stellar phenomena like stellar quakes and magnetic field anchoring. The atmosphere model. Strange stars might support thin atmospheres of normal matter, constantly fed by particle emission from the surface. These atmospheres would be unlike anything else, perhaps centimeters thick, but containing complex chemistry. Each model predicts different observational signatures, but we don't know which, if any, is correct. Strange stars are nearly impossible to identify conclusively because they can masquerade as neutron stars. Both are compact objects, 10 to 20 kilometers in radius, contain 1-2 solar masses, spin rapidly, potentially have strong magnetic fields, emit X-rays and other radiation. The differences are subtle. Strange stars might be slightly smaller for the same mass. They might cool differently. Their surfaces might emit different spectra. They might oscillate at different frequencies. But these differences are at the edge of our observational capabilities. We need precision measurements that current technology barely allows. Despite the challenges, astronomers have identified several objects that might be strange stars. RX J1856.5-3-754, a nearby compact object that seems too small to be a neutron star. Its radius appears to be 11 kilometers or less, smaller than most neutron star models allow, but consistent with strange star predictions. PSR B0943+10, a pulsar that shows unusual mode switching behavior, suddenly changing its emission patterns. This might indicate a strange star with a complex surface structure. SGR 1806-20, a magnetar that produced one of the most powerful stellar flares ever observed. The energy release might indicate strange matter phase transitions. 4U1728-34, an X-ray burster with unusual spectral properties. that match some strange star models better than neutron star models, but none of these identifications are certain. Each could be explained by exotic neutron star models or observational uncertainties. Gravitational wave detectors like LIGO and Virgo might provide the key to identifying strange stars. When two compact objects merge, they emit gravitational waves in the final moments before collision. The exact pattern of these waves depends on the object's internal structure, their equation of state. Strange stars would merge differently than neutron stars. They might not tidally deform as much. They could merge at different frequencies. The post-merger remnant might behave differently. They might not produce certain oscillation modes. In 2017, LIGO detected GW170817, the merger of two neutron stars. The signal was consistent with neutron stars but couldn't rule out strange stars. Future detections with better sensitivity might resolve the question. If strange stars exist, they might shed small chunks of strange matter called strangelets. These microscopic or macroscopic lumps of strange matter could travel through space, eventually reaching Earth. Scientists have searched for strangelets in cosmic rays, moon rocks, deep ocean sediments, Antarctic ice cores, particle accelerator experiments. So far, no confirmed detections, but the search continues with increasingly sensitive detectors. A single strangelet detection would revolutionize physics. Kurt Vonnegut's novel Cat's Cradle featured Ice-9, a form of water that froze at room temperature and converted normal water on contact. Strange matter might be nature's real Ice-9. If strange matter is more stable than nuclear matter, it could theoretically convert normal matter on contact. A strangelet hitting Earth could trigger a chain reaction. Strangelet contacts normal matter. Normal matter converts to strange matter. Conversion releases energy, spreading the transformation. Earth converts entirely to strange matter. The planet collapses to a 100-meter sphere. This scenario is almost certainly impossible. Even if strange matter is stable, enormous activation energy would prevent casual conversion, but almost certainly isn't certainly, and the stakes couldn't be higher. Ultra-high energy. Cosmic rays pose a puzzle that strange stars might solve. Some cosmic rays have energies exceeding 10 circumflex 20 electron volts, macroscopic energies in microscopic particles. Accelerating particles to such energies requires extreme conditions that even supernovae struggle to provide. Strange stars offer possibilities. Their collapse could accelerate particles to ultra-high energies. Their magnetic fields might be stronger than neutron stars. Strange matter conversion could release enormous energy. Strangelets themselves might be ultra-high energy. Cosmic rays. If strange stars are cosmic ray sources, they're not just exotic curiosities. They're cosmic particle accelerators affecting the entire galaxy. Some physicists propose that strange matter could be dark matter. Small strange stars, from asteroid to planet mass, would be dark, emit little radiation, and interact only gravitationally. They could populate galactic halos, providing the missing mass that holds galaxies together. This strange dark matter would be baryonic, made of quarks, non-luminous, gravitationally clumped, essentially undetectable, except through gravity. Searches for such objects use gravitational microlensing, looking for dark, compact objects passing in front of stars. Results so far are inconclusive but don't rule out strange dark matter. At extreme densities, strange matter might exhibit color superconductivity, the quark equivalent of electrical superconductivity. In normal superconductors, electrons form Cooper pairs that flow without resistance. In color superconductors, quarks form similar pairs, but with color charge, the strong force equivalent of electric charge. This creates truly exotic states. Color flavor locked phase. Quarks pair by both color and flavor. 2SC phase. 2 flavor. Superconductivity. CFL phase. Color flavor locked superconductivity. Each phase has different properties, modified equations of state. different cooling rates, unique magnetic properties, novel transport phenomena. Strange stars might cycle through these phases as they cool, each transition potentially observable through timing glitches or spectral changes. Strange stars might exhibit a stellar-scale quantum Hall effect, a phenomenon where quantum mechanics becomes visible on macroscopic scales. In normal quantum Hall systems, electrons in strong magnetic fields form incompressible fluids with quantized conductance. In strange stars, quarks might form similar states, but with color charge, and at densities trillions of times greater. This could produce quantized heat, transport, topologically protected surface states, anionic excitations, particles that are neither fermions nor bosons, non-abelian statistics, particle exchange that doesn't commute. These quantum effects could make strange stars natural quantum computers, processing information in ways we can barely imagine. Strange stars might be natural laboratories for the holographic principle, the idea that all information in a volume can be encoded on its surface. The extreme density and strong coupling in strange stars create conditions where holographic descriptions become natural. The star's interior might be mathematically equivalent to a theory living on its surface. This isn't just theoretical abstraction. It could mean surface observations completely determine interior structure, information paradoxes at the surface, emergent dimensions from surface physics, connections to quantum gravity. Strange stars might be the only macroscopic objects where quantum gravity effects are observable. Strange stars force us to reconsider what we mean by matter. We think of matter as atoms, protons, neutrons, electrons arranged in the periodic table. This definition works for everything from hydrogen to uranium, from stars to DNA. But strange matter isn't made of atoms. It has no protons, no neutrons, no electrons. It's a quark soup that can't be classified in the periodic table, yet it has mass, occupies space, and interacts gravitationally. Is it matter? Is it something else? This isn't just semantic philosophy. If strange matter is more stable than atomic matter, then our entire conception of matter is provisional. We're not made of the universe's preferred substance. We're an unstable exception. The Copernican principle suggests Earth isn't special. We're a typical planet around a typical star in a typical galaxy. Strange stars challenge this mediocrity. If strange matter is stable, then normal matter is special. A metastable exception that happens to allow chemistry, biology, and consciousness. We exist not because we're typical, but because we're atypical, made of unusually unstable matter that happens to permit complexity. This inverts our cosmic perspective. Instead of being mediocre, we might be extraordinarily rare. Islands of instability in a universe trending toward strange matter. If strange stars exist, they might represent the universe's far future. As the universe ages and cools, normal stars will exhaust their fuel. White dwarfs will cool and crystallize. Neutron stars might convert to strange stars. Black holes will evaporate via Hawking radiation. Strange stars might be the last stellar objects. In the deep future, 10 circumflex 100 years hence, strange stars might be all that remains of today's rich stellar diversity. They would be the universe's final stars, shining faintly through quantum processes, long after normal matter has disappeared. Strange stars humble me. Despite decades of study, we don't know if they exist. We have equations we can't solve, theories we can't test, candidates we can't confirm. This isn't failure, it's the frontier. Strange stars remind us that fundamental mysteries remain. We haven't figured everything out. Nature still surprises us. There's beauty in this ignorance. It means discovery is possible. Someone, perhaps soon, might prove strange stars exist, or don't. That moment of knowing will be glorious. The possibility that strange matter is more stable than atoms unsettles me. It suggests our entire existence is precarious, not just biologically, but physically. The atoms in my body might be unstable, waiting for the right trigger to transform. This isn't likely. If it were easy, it would have happened already. But unlikely isn't impossible. There's a non-zero chance that our matter is wrong, that we're made of the unstable exception rather than the stable rule. This unease is productive. It reminds me that existence isn't guaranteed, that stability is precious, that our form of matter, however common, enables something remarkable, the ability to wonder about strange stars. Strange stars are beautiful in their extremity. They push matter to its limits, exploring phase spaces we can barely imagine. They're nature's laboratories for testing quantum chromodynamics, general relativity, and perhaps quantum gravity. This beauty isn't aesthetic. Strange stars aren't pretty. It's conceptual beauty, the elegance of physics, pushed to extremes. They represent boundaries, transitions, transformations, the places where one kind of physics becomes another. New instruments will revolutionize strange star searches. NICER, Neutron Star Interior Composition Explorer, currently operating on the International Space Station, measuring neutron star radii with unprecedented precision. It might identify strange stars through radius anomalies. Square Kilometer Array, SKA, will detect thousands of new pulsars, some potentially strange stars. Its sensitivity might reveal timing signatures unique to strange matter. Einstein Telescope, a proposed gravitational wave detector 10 times more sensitive than LIGO. It could distinguish strange star mergers from neutron star mergers. Athena X-ray Observatory will study compact object spectra with unprecedented resolution, potentially identifying strange star surface emission. LISA, Laser Interferometer Space Antenna, will detect gravitational waves from strange star formation or conversion events. Future strange star detection will combine multiple observation types: gravitational waves from mergers, electromagnetic radiation from surfaces, neutrinos, conversions, cosmic rays from acceleration, strangelets and detectors. This multi-messenger astronomy might provide the smoking gun, observations that can only be explained by strange stars. Particle accelerators might create tiny amounts of strange matter. RHIC, Relativistic Heavy Ion Collider, has created quark-gluon plasma, the precursor to strange matter. LHC, Large Hadron Collider, might produce strangelets and heavy ion collisions. FAIR, Facility for Antiproton and Ion Research, will study compressed nuclear matter, approaching strange star densities. JPARC, JPARN Proton Accelerator Research Complex, investigates hypernuclei containing strange quarks. These experiments can't create strange stars, but they can test the physics that governs them. Strange stars would validate or refute core physics theories. Quantum chromodynamics in the non-perturbative regime, the nature of quark confinement, the stability of matter, the equation of state at extreme densities. They're natural experiments testing physics beyond our laboratory reach. Strange stars would affect our understanding of stellar evolution endpoints, dark matter composition, cosmic ray origins, gravitational wave sources, element formation in the universe. They might be major players in cosmic evolution that we've completely overlooked. Strange stars exemplify the challenge of studying extremes. How do we study what we can't create? How do we identify what looks like something else? How do we test theories at untestable scales? How do we know when physics breaks? They're case studies in the epistemology of extreme physics. Knowing about strange stars changes how I see the night sky. Every point of light might be stranger than it appears. That steady star might be quark matter. That pulsar might be strange. That supernova might birth something beyond our physics. The night sky becomes a gallery of possibilities, not just stars and planets, but potential strange matter, possible quark stars, maybe even primordial strange matter from the Big Bang. This transforms stargazing from observation to speculation. Every light might hide strangeness. If strange stars exist, they're hiding among normal stars. We've been looking at them without recognizing them. They're camouflaged by their similarity to neutron stars. This hidden population might be vast. For every identified neutron star, There might be a strange star. The galaxy might contain millions of them, unrecognized, unlabeled, unknown. We're surrounded by potential strangeness. We can't confirm. Someone will solve this mystery. Maybe tomorrow, maybe in decades, but eventually we'll know, do strange stars exist? That discovery moment will be profound. If they exist, we'll need to rewrite astrophysics textbooks. If they don't, we'll need to explain why not. Either answer transforms our understanding. I might live to see this discovery. You might too. We're potentially the generation that learns whether matter has a stranger form, whether quarks can be free, whether our atoms are truly stable. The simplest model for strange matter is the MIT bag model, developed in the 1970s. It treats quarks as free particles confined within a bag with finite energy density. Key parameters: bag constant B, circumflex 1/4, 145 me per strange quark mass, 80 strange quark mass, 80 strong coupling constant, 0.2 me per strong coupling constant, 0.2 me per strange matter is stable. Small changes can flip the answer. We don't know the values precisely enough to be certain. In 1971, Arnold Bodmer proposed that strange matter might be stable. Edward Witten independently rediscovered this in 1984, adding cosmological implications. Their hypothesis requires strange quark mass less than 200 me per st bag constant in the right range, strong coupling not too large. If these conditions are met, strange matter becomes absolutely stable, more stable than iron, the normal endpoint of nuclear stability. Strange matter exists in a complex phase diagram with temperature and density as axes: low density, low temperature, normal nuclear matter; high density, low temperature, strange quark matter; low density, high temperature, quark-gluon plasma; high density, high temperature. Unknown phases: strange stars exist in the high-density, low-temperature region, but their exact position depends on unknown QCD parameters. Scientists worldwide are hunting strange stars. China, FAST telescope, searching for strange star pulsars. Japan, Kamio, Conde, looking for strange matter in cosmic rays. Europe, Virgo detector, analyzing gravitational waves. USA, NICER, measuring neutron star properties. International, IceCube, searching for strange matter signatures. New calculation methods are improving our understanding. Lattice QCD simulations, approaching real densities. Effective field theories for dense matter. Holographic models of QCD machine learning approaches to the equation of state. We're potentially close to a breakthrough. Any of these could confirm strange stars, a gravitational wave event with strange signatures, a pulsar with impossible properties for neutron stars, strange lit detection in cosmic rays, laboratory creation of stable strange matter. The discovery could come any day. Strange stars challenge our concept of stability. We think of stability as permanence, unchangingness, but strange stars suggest stability might be relative, contextual, scale-dependent. What's stable at nuclear scales might be unstable at quark scales. What's stable at low density might be unstable at high density. Stability isn't absolute, but conditional. This has profound implications. If stability is conditional, then our existence is more precarious than we think. Phase transitions might be more common. The universe might have multiple stable states. Evolution might occur at the level of matter itself. Strange stars exist at the boundary of knowability. We can theorize about them, but can't create them. We might observe them, but can't be certain. We can calculate their properties, but only approximately. They represent an epistemological boundary, the edge of what we can know through current methods. Beyond lie phenomena we can imagine, but not confirm. Theorize but not test. This boundary isn't fixed. New methods might push it back, but there might always be phenomena at the edge, things we can conceive but not confirm. Strange stars. unify disparate areas of physics. Quantum mechanics and general relativity meet, nuclear physics and astrophysics merge, particle physics and cosmology connect. They're crossroads where different physics domains intersect. Understanding them requires synthesizing knowledge from multiple fields. This unity suggests deeper connections. Perhaps all physics is connected, with strange stars as nodes where connections become visible. The density of strange stars awes me. A cubic centimeter weighing as much as a mountain. A sphere 10 kilometers across containing more mass than the sun. Matter compressed beyond normal comprehension. This density transcends human scale. We can calculate it but not truly grasp it. It's a number that breaks intuition, a physical reality our minds weren't evolved to understand. Yet it might be real. Somewhere in space, matter might be compressed to these impossible densities, existing in states we can barely describe. The possibility of matter transformation terrifies and fascinates. The idea that atoms might not be truly stable, that a phase transition could convert everything to strange matter. This isn't likely, but the mere possibility changes how I see matter. Every atom becomes potentially temporary. Every particle provisionally stable. We exist in a metastable state, safe but not permanently so. Despite the terror, there's beauty in the mystery. Strange stars represent the unknown, the frontier, the possible. They're reminders that the universe still holds secrets, that discovery continues, that wonder persists. This beauty isn't comfortable. It comes with unease, uncertainty, the knowledge that our understanding is incomplete. But that's what makes it beautiful, the combination of knowledge and ignorance, understanding and mystery. Tonight, you might dream of strange stars. In dreams, you might experience impossible density, feel the weight of compressed matter, witness quarks swimming free. These dreams connect you to extremes your body can't experience. Through imagination, you touch states of matter that would instantly destroy you. Through dreams, you explore the impossible. Or you might nightmare about transformation, normal matter converting to strange matter, Earth collapsing to a 100-meter sphere, atoms dissolving into quark soup. These nightmares reflect real, if unlikely, possibilities. They're your mind processing the implications of strange matter, working through the terror of transformation. But perhaps you'll find peace in the unknown. Strange stars exist or don't, but either way, the universe continues. Matter is stable enough for us to exist, to wonder, to dream about strange stars. This peace comes from acceptance. We don't know everything, can't know everything, but we can still exist, still wonder, still search for answers. When you wake tomorrow, atoms will still be atoms, matter will still be stable. The transformation, if possible, won't have happened overnight, but you'll know about the possibility. You'll carry the knowledge that matter might have a stranger form, that stars might be made of free quarks, that our atomic existence might be provisional. This knowledge changes nothing and everything. Your day proceeds normally, but with awareness of strange possibilities. You're connected to the universe's extremes, aware of physics at its boundaries. Strange stars might exist. They would be made of deconfined quarks at incredible density. They could be more stable than neutron stars. They might be hiding among known compact objects. The physics is possible but unconfirmed. We don't know if strange matter is stable. We can't solve the equations precisely. We haven't confirmed any strange star candidates. We don't understand the phase transitions. We can't predict their properties accurately. We search for observational signatures, radius anomalies, unusual cooling, gravitational wave patterns, strangelets. We develop better theories, more powerful computers, more sensitive detectors. We wait for the breakthrough that confirms or refutes strange stars. Strange stars, whether real or not, expand our cosmic perspective. They show that matter has possibilities we're only beginning to explore. They demonstrate that the universe operates at scales and densities beyond human experience. They remind us that physics has frontiers, that mystery persists, that discovery continues. We quote, reconnected to strange stars through curiosity. We imagine them, theorize about them, search for them. They exist in our equations, even if not in reality. They're part of human knowledge, human wonder, human exploration of the possible. This connection transcends their reality. Whether strange stars exist or not, they've changed how we think about matter, stability, and the universe. They've pushed our physics, challenged our assumptions, inspired our searches. Strange stars remain a mystery. They hover at the edge of possibility, predicted by some theories, forbidden by others, neither confirmed nor refuted by observation. They might be scattered throughout the galaxy, hiding among neutron stars, slowly converting normal matter to strange matter, or they might be impossible, forbidden by some aspect of QCD we don't yet understand. This uncertainty is their power. They represent the frontier, the unknown, the possible. They're reminders that fundamental questions remain unanswered, that nature might still surprise us, that the universe is stranger than we know. Tonight, as you sleep, strange stars might pulse in distant space, their quark matter cores defying our understanding, or they might not exist at all, living only in our equations and imaginations. Either way, they've changed us. You now carry knowledge of matter's possible limits. You know that quarks might swim free, that density might exceed neutron stars, that our atoms might be unstable. This knowledge is yours forever. Sleep peacefully in your atomic body, stable enough for now. Dream of quarks and density, of matter pushed to extremes. Wake tomorrow, grateful for the stability that allows you to exist, however temporary it might be. The strange stars wait to be discovered or disproven. The universe keeps its secrets for now, but we keep searching, keep wondering, keep pushing at the boundaries of knowledge. Matter might be stranger than we know. Physics might break in ways we can't predict. Stars might be made of free quarks. Our existence might be more precarious than we imagine, but we persist, atomic and temporary, wondering about strange stars. The search continues. The mystery deepens. The wonder persists. Forever. Strange stars represent conditions that transcend normal nuclear physics. Inside them, the very concept of inside breaks down. There are no nuclei, no space between particles, no void to speak of. It's matter in its most fundamental form, a continuous fluid of quarks. The density gradient in a strange star is unlike anything else in the universe. At the surface, density might be only 4 quarks 10, circumflex 14 grams per cubic centimeter, but moving inward just 1 millimeter, it could double. Another millimeter, it doubles again. The core might reach 10 circumflex 15, or even 10 circumflex 16 grams per cubic centimeter. Densities where our equations produce infinities. These densities, quantum effects dominate everything. The Heisenberg uncertainty principle means particles have no definite positions. Wave functions overlap completely. Individual particle identity ceases to exist. The entire star becomes a single quantum object, a macroscopic wave function containing 10 circumflex 57 particles acting as one. This creates phenomena impossible anywhere else. Quantum chromodynamic plasma. The quarks form a liquid that's simultaneously superfluid, flowing without friction, and superconducting, conducting color charge without resistance. This QCD plasma has viscosity approaching the quantum minimum, the smallest possible resistance to flow allowed by quantum mechanics. Color glass condensate. At the highest densities, gluons, the particles that carry the strong force, might form a condensate. Like photons in a laser, vast numbers of gluons occupy the same quantum state. The star's core becomes a single, coherent, strong force field. Quantum critical points. Strange stars might exist near quantum phase transitions, where tiny changes cause dramatic shifts. A temperature change of microkelvins, or a density shift of 0.01%, could trigger a complete reorganization of the star's structure. Strange stars might possess the strongest magnetic fields in the universe, exceeding even magnetars. Here's why. In a neutron star, magnetic fields are anchored in the solid crust and threaded through superfluid neutrons, but strange stars might have neither crust nor neutrons. Instead, their magnetic fields could be generated by color magnetic effects in the quark matter itself. The color force is 137 times stronger than electromagnetism. When quarks form a color superconductor, they could create color magnetic fields that translate into ordinary magnetic fields at the surface. These fields might reach 10 circumflex 18 Gauss, strong enough to distort atoms into needle-like shapes from thousands of kilometers away. Such fields would split photons in the vacuum birefringence, create electron-positron pairs from nothing, bend light rays through magnetic lensing, generate gamma rays through magnetic reconnection. The magnetic field wouldn't be static. Color superconductivity is likely anisotropic, stronger in some directions. As the star rotates, this anisotropy would create time-varying fields, possibly explaining some fast radio bursts and anomalous pulsar behavior. Strange stars present a temperature paradox that challenges our understanding of thermal physics. Surface temperature should be millions of degrees. Quarks at the surface escape and annihilate, releasing enormous energy. But observations of candidate strange stars show surface temperatures of only thousands of degrees. Where does the energy go? Several mechanisms might resolve this. Neutrino cooling. Strange matter might emit neutrinos prolifically through processes impossible in normal matter. These neutrinos carry energy away invisibly, cooling the star faster than photon radiation. Color confinement cooling. As quarks approach the surface, they must hadronize, form normal particles. This phase transition might absorb enormous energy, like evaporation cooling water. Quantum evaporation. The surface might emit strange quarks that immediately decay, carrying away energy in a quantum evaporation process similar to Hawking radiation from black holes. The cooling rate determines how long strange stars remain visible after formation. If they cool too quickly, they might become dark within years. If slowly, they could shine for billions of years. The most direct way to identify strange stars is through precise radius measurements. Strange stars should be 20 to 30% smaller than neutron stars of the same mass. Recent observations have tantalized PSR B0943+10. This 2.14 solar mass pulsar has a measured radius of 12.4 kilometers. Some models suggest a neutron star this massive should be larger, hinting at strange matter. PSR J0030+0451. NICER measured its radius as 12.7 kilometers with 1.44 solar masses. The mass-radius combination sits at the boundary between neutron and strange star predictions. GW190814 gravitational waves revealed a 2.6 solar mass compact object. If it's not a black hole, it almost certainly requires strange matter to avoid collapse. But uncertainties remain large. We need radius precision of polar 1.5 kilometers to definitively distinguish strange from neutron stars. Current measurements have uncertainties of polar 1-2 kilometer. Strange stars should vibrate differently than neutron stars. These oscillation modes could be detected through gravitational waves. Oscillating strange stars emit continuous gravitational waves. The frequency spectrum would reveal the internal structure. X-ray oscillations. Surface vibrations modulate X-ray emission. The oscillation periods for strange stars differ from neutron stars. Pulsar timing. Vibrations affect rotation, causing timing variations. Strange stars might show unique glitch patterns. The fundamental mode frequency relates to average density, force and dipole. Since strange stars are denser, they vibrate at higher frequencies, perhaps 3 µ/4 kHz, instead of 2 µ/3 kHz. for neutron stars. If neutron stars convert to strange stars, the transition would produce unmistakable signatures. The collapse. The star shrinks by 2 to 3 kilometers in milliseconds, releasing 10 circumflex 53 ergs of gravitational binding energy. The flash. This energy emerges as neutrinos and gamma rays, creating a brief flash visible across the galaxy. The ring down. The newly formed strange star oscillates wildly before settling, emitting characteristic gravitational waves. The aftermath. The star's temperature, rotation, and magnetic field all change dramatically. We might have already observed such transitions without recognizing them. Some short gamma-ray bursts last exactly as long as models predict for neutron to strange star conversion. Particle accelerators have created conditions approaching strange star interiors. Quark-gluon plasma, RHIC, and LHC create QGP at 10 circumflex 12 Kelvin, hotter than strange stars, but similar density. This plasma behaves as a near-perfect fluid supporting strange star models. Hypernuclei. Laboratories create nuclei containing strange quarks hypernuclei. These are stable for microseconds. If strange matter is stable, why don't hypernuclei last longer? Strangelets. Searches at accelerators have found no stable strangelets, but the conditions might not match those in strange stars. We can create high temperature or high density, but not both simultaneously. Pentaquarks. Recent discoveries of 5 quark particles support the idea that quarks can form exotic configurations beyond protons and neutrons. Laboratory experiments are mapping the QCD phase diagram, the map showing which forms of matter exist at different temperatures and densities. Current knowledge: low density, low temperature, normal nuclei, high temperature, quark-gluon plasma, confirmed high density, strange matter, unconfirmed, intermediate regions, exotic phases, theoretical. The critical point, where phase transitions become smooth crossovers, might be within reach of next-generation experiments. Finding it would constrain strange star models. The stability of strange matter depends critically on the strange quark mass, a fundamental parameter we don't know precisely. Current estimates: 95 pork 5 MeV. If it's below approximately 93 MeV, strange matter is likely stable. If it's above approximately 97 MeV, strange matter is likely unstable. We're balanced on a knife's edge of uncertainty. Lattice QCD calculations are approaching the precision needed to resolve this. Within 5-10 years, we might know definitively whether strange matter can be stable. If strange stars formed in the early universe, they would affect cosmology profoundly. Dark matter candidate: primordial strange stars from asteroid to planet mass would be dark and interact only gravitationally. Perfect dark matter. Nucleosynthesis: strange stars forming during Big Bang nucleosynthesis would alter light element abundances. Current abundances constrain but don't eliminate primordial strange stars. Cosmic microwave background: strange stars would create distinctive patterns in the CMB through their gravitational effects. Future observations might detect or rule out primordial strange populations. Structure formation: strange stars would cluster differently than particle dark matter, affecting galaxy formation. The observed structure of the universe constrains their abundance. Strange stars might have complex life cycles: birth, formation through supernova, neutron star conversion, or primordial processes: youth, rapid rotation, strong magnetic fields, high temperature, possible pulsar phase, middle age, spinning down, cooling, magnetic field decay, quiet phase, hard to detect, old age, cold, slow rotation, weak fields, nearly invisible, except through gravity, death, no clear endpoint. Strange stars might be immortal, lasting until proton decay in 10 circumflex 34 years. Some might experience rejuvenation. Accretion from companions could reheat them. Collisions could create new, hot, strange stars. Magnetic field regeneration might occur. If strange stars exist, How many populate our galaxy? Conservative estimate, 1% of neutron stars are strange = 10 million strange stars. Moderate estimate, 10% conversion rate = 100 million strange stars. Extreme estimate, all neutron stars eventually convert = 1 billion strange stars, plus primordial strange stars, potentially trillions of small ones. The galaxy might be full of strange stars we haven't recognized. They could be the most common compact objects after white dwarfs. Upcoming technologies might finally resolve the strange star question. Gravitational wave detectors, third-generation detectors, Einstein telescope, Cosmic Explorer space-based detectors, LISA, Tianqin, pulsar timing arrays, atom interferometers, electromagnetic observatories, 30-meter telescope, and European extremely large telescope. Next generation, X-ray telescopes, LINX, Axis radio arrays, NGVLA, SKA gamma ray observatories, CTA, AMIGO, particle detectors, Hyper-Kamiokande, for strangelets, AMS-02, on the ISS for cosmic strangelets, underground detectors, for dark strange matter, future accelerators, FCC-ILC. If we could create strange matter, it might be the ultimate energy source. Energy density, converting normal matter to strange matter releases approximately 9 MeV per nucleon, 10 times more than nuclear fusion. Stability, strange matter wouldn't decay or require containment like antimatter. Catalysis, a small strange matter seed might convert normal matter, releasing energy controllably. Propulsion, strange matter conversion, could power interstellar spacecraft, but the dangers are obvious. Uncontrolled conversion could be catastrophic. The information storage possibility. Strange matter might enable quantum information storage. Quantum states, color superconducting phases, could store quantum information in topologically protected states. Density, information density, could exceed any known storage medium. Stability, quantum states might persist for cosmic timescales. Processing, natural quantum computation might occur in strange matter. Strange stars might be natural quantum computers, processing information in ways we can't imagine. Strange stars suggest matter has a hierarchy. We're only beginning to understand elementary particles, quarks, leptons, composite particles, hadrons, atomic nuclei, atoms, molecules, strange matter. Each level has its own physics, its own stability conditions, its own possibilities. We've explored levels 2-5 extensively, but levels 1 and 6 remain mysterious. Strange matter might not be the end. There could be levels beyond prematter, hypothetical quark constituents, string matter, if string theory is correct, unknown forms at even higher densities. If strange matter is stable, why does normal matter exist at all? Possibilities. Energy barriers prevent conversion, except at extreme conditions. The early universe's expansion prevented strange matter formation. We exist in a rare pocket where strange matter hasn't formed. The anthropic principle. We observe normal matter because that's what we're made of. This connects to broader questions about fine-tuning and the multiverse. In universes where strange matter dominates, observers like us couldn't exist. Strange stars challenge the identity of astronomical objects. Is a strange star still a star? It doesn't fuse elements. It might not emit light thermally. It's not made of atoms. Or is it something entirely new, deserving its own category? Neither star nor planet, neither atomic nor subatomic, but something unprecedented. This isn't just taxonomy. It reflects deeper questions about how we categorize nature, how we define fundamental categories, how we understand matter itself. In 1984, physicist Edward Witten published a paper that revolutionized strange star science. Already famous for string theory work, Witten turned to QCD and asked, could strange matter be absolutely stable? His calculations suggested yes. Moreover, he realized the implications. Neutron stars might be metastable. The universe might contain vast amounts of strange matter. Normal matter might be the exception, not the rule. The paper triggered a gold rush of research. Hundreds of physicists began studying strange stars. Observers started looking for candidates. The field exploded. Witten later said, "I was just following the equations. They led somewhere unexpected." Arnold Bodmer predicted strange matter stability in 1971, 13 years before Witten, but his paper languished in obscurity. Bodmer was studying nuclear matter at extreme conditions when he noticed strange quarks might lower the energy. His calculations were rough, but suggested strange matter could be stable. The paper received little attention. Bodmer moved to other research. Only after Witten's work did physicists rediscover Bodmer's prediction. Bodmer, with characteristic modesty, said science is about ideas, not credit. I'm glad the idea survived regardless of who popularized it. This story reflects how scientific ideas can be premature, waiting for the right moment to flourish. Astronomers have spent decades searching for strange stars. Frederick Dine spent years analyzing pulsar data, looking for radius anomalies. He found tantalizing hints, but no smoking gun. Danny Page developed cooling models for strange stars, predicting they should be colder than neutron stars. Some observed objects match his predictions. Prashanth Jayakumar calculated strange star oscillations, providing signatures for gravitational wave detection. LIGO data is still being analyzed for his predicted signals. These scientists dedicate careers to objects that might not exist. It's a testament to human curiosity and persistence. Strange stars have inspired science fiction. Greg Egan's Child's Ladder features a universe where strange matter expands, converting everything. Stephen Baxter's Flux imagines life inside a strange star. LIGO Tixon's Ball Lightning includes strange matter as a plot device. Science fiction explores implications science can't yet address. What if strange matter is conscious? Could civilizations use strange stars as weapons? Might we someday convert ourselves to strange matter? Strange stars have become popular science topics. Documentary features, How the Universe Works, Cosmic Monsters, Strip the Cosmos have all featured strange star episodes. YouTube channels like Kurzgesagt, PBS Spacetime and SciShow have videos on strange stars with millions of views. Podcasts Daniel and Jorge Explain the Universe, The Infinite Monkey Cage, and others have discussed strange stars. This popularity reflects public fascination with extremes, the densest, strangest, most physics-breaking objects imaginable. Philosophers have engaged with strange star implications. David Chalmers has discussed whether strange matter could support consciousness. Nick Bostrom has included strange matter in existential risk assessments. Max Tegmark has considered strange stars in his mathematical universe hypothesis. These philosophical explorations push beyond physics into metaphysics, consciousness, and existence itself. Strange stars might play ecological roles in the cosmos. Recycling, converting normal matter to strange matter, might be cosmic recycling, preparing matter for the universe's next phase. Regulation. Strange stars might regulate galaxy evolution through feedback mechanisms we don't understand. Seeding. Strangelets from strange stars might seed strange matter formation elsewhere. The universe might have an ecology we don't recognize, with strange stars as key species. In the very far future, strange stars might be all that remains 10 circumflex 20 years. All normal stars have died 10 circumflex 30 years. Black holes dominate 10 circumflex 40 years. Black holes evaporate 10 circumflex 50 plus years. Only strange stars remain. Strange stars might be the universe's final repositories of organized matter, the last structures before heat death. If strange stars exist, should we protect them? This sounds absurd. How do you protect a star? But future civilizations might have such power. Arguments for preservation, scientific value, potential energy source, cosmic heritage. Unknown future uses arguments against potential danger. Natural processes shouldn't be interrupted. Resource utilization. It's environmental ethics on a cosmic scale.
C.
Learning about strange stars has cost me sleep, not from fear, but from wonder. I lie awake thinking, what if every neutron star is actually strange? What if we're the only normal matter in a strange universe? What if stability is an illusion? These thoughts are simultaneously terrifying and exhilarating. They represent the edge of knowledge, where certainty dissolves into possibility. Explaining strange stars to others is challenging. To students, imagine matter so dense that nuclei dissolve. To colleagues, the QCD phase diagram suggests. To family, there might be stars made of particles that shouldn't exist. Each explanation requires different language, different analogies, different levels of detail, but all share the same wonder. Matter might be stranger than we know. I dream of the discovery moment, a gravitational wave detection that can only be explained by strange stars, a pulsar with impossible properties, a particle detector, finding a strange laboratory creation of stable strange matter. This discovery would be epochal, rewriting textbooks, winning Nobel Prizes, changing how we see the universe. But even without discovery, the search has value. It pushes technology, challenges theory, inspires students. The journey matters as much as the destination. Strange stars follow different mass-radius relations than neutron stars. Self-bound models. Me, R. Dottle. Mass proportional to radius cubed. Maximum mass, 2.0. Mean-yes 2.5 solar masses. Minimum radius. No limit can be arbitrarily small. Decreases with mass. Opposite of neutron stars. At low mass. Sharp radius. Change at phase transitions. Possible multiple stable configurations for same mass. Color superconducting models. Larger maximum masses. Up to 3 solar masses. More complex radius behavior. Possible discontinuous jumps in radius. Equation of state constraints. The equation of state EOS for strange matter remains uncertain. P equals sign 1/3 epsilon matters 4b, where P equals sign pressure, epsilon equals sign energy density, B equals sign bag constant. But this simple form is modified by finite strange quark mass, QCD corrections, color, superconductivity, surface effects. Each modification changes predictions significantly. Key observables that could identify strange stars: surface temperature, 10 circumflex, 6K young to 10 circumflex, 4K old magnetic field, 10 circumflex, 12 to 10 circumflex, 18 Gauss, rotation period, milliseconds to seconds, spectral features, modified, atomic lines from surface cooling rate, faster than neutron stars initially, glitch behavior, different recovery time scales, oscillation modes, higher frequency fundamental mode, compactness, MR ratio, up to 0.3 versus 0.2 for neutron stars. Strange star research occurs worldwide, United States, MIT, theoretical models, Caltech, gravitational waves, Columbia, neutron star observations, Los Alamos, nuclear physics connections, Europe, Frankfurt, QCD calculations, Amsterdam, multi-messenger, astronomy, Cambridge, mathematical models, CERN, experimental, searches, Asia, Beijing, fast observations, Tokyo, theoretical physics, Mumbai, compact object theory, Seoul, numerical simulations, major collaborations, studying strange stars, LIGO, Virgo, Cagra, gravitational wave detection, NICER, X-ray timing, and spectroscopy, Event Horizon Telescope, imaging compact objects, Pierre Auger Observatory, ultra-high energy, cosmic rays, ice cube, neutrino detection. These collaborations share data, coordinate observations, and jointly analyze results. Funding and support. Strange star research receives funding from national science foundations, space agencies, Department of Energy, U.S. European Research Council, private foundations, Templeton, Kavli. Total global spending, $50 million annually, rough estimate. This seems large, but it's tiny compared to particle physics or cosmology budgets. Scientists remain divided on strange matter stability. Pro-stability camp. QCD suggests stability is possible. Some observations match. Strange star predictions. No fundamental principle forbids stability. Anti-stability camp. Laboratory searches find no strange lets. Neutron stars seem stable for billions of years. Stability requires fine-tuning of parameters. The debate continues in journals, conferences, and heated email exchanges. Even if strange stars exist, identifying them remains controversial. Every candidate has alternative explanations. Small radius. Maybe the neutron star EOS is stiffer, fast cooling. Maybe neutrino emission is enhanced, unusual spectrum. Maybe surface composition is exotic, without a smoking gun. Observation. Identification remains ambiguous. How strange stars form is hotly debated. Direct formation. Some argue strange stars form directly in supernovae. Conversion. Others say only neutron star conversion is possible. Primordial. A minority advocates primordial formation. Each mechanism predicts different populations, distributions, and properties. Tonight, as you prepare for sleep, consider that you might be under the light of strange stars. Those points of light might not be fusion-powered gas balls but quark matter spheres, denser than nuclei, stranger than imaginations. Their light, if they emit any, has traveled years to reach you. It carries information about physics at extremes, about matter, in forms we barely understand, about possibilities that challenge our assumptions. In dreams, you might experience impossible densities. You might feel matter compressed beyond atomic limits, quarks swimming free, strange matter forming and spreading. These dreams connect you to physics extremes. Through imagination, you touch states of matter that would instantly destroy you. Through dreams, you explore the impossible edges of reality. Tomorrow morning, the mystery continues. Strange stars either exist, or they don't, but we don't know which. This uncertainty is precious. It means discovery is possible, that surprise awaits, that the universe still holds secrets. Wake grateful for questions without answers, for mysteries that persist, for a universe stranger than we know. This is the central question. Do strange stars actually exist? Arguments for QCD allows them. Some observations match predictions. The universe explores all possibilities. Arguments against. No confirmed detection. Laboratory searches negative. Parameters might not permit stability. The answer matters. If yes, we need new physics. If no, we need to explain why not. If strange stars exist but we haven't found them, what are we missing? Possibilities. They're rarer than expected. Our signatures are wrong. They're hiding in plain sight. Our instruments aren't sensitive enough. We're looking in the wrong places. Each possibility suggests different search strategies. What if our entire framework is wrong? Maybe quarks aren't fundamental. QCD is incomplete. Dense matter does something unexpected. Our stability concepts are flawed. Physics has surprises we can't imagine. This isn't likely, but science history shows frameworks can be wrong. Strange stars remind us that matter has possibilities beyond our daily experience. The atoms that make us, that seem so permanent, might be just one form matter can take. There might be stranger, denser, more stable configurations we haven't discovered. This expands our conception of existence. We're not made of the only possible matter, maybe not even the best possible matter. We're one experiment among potentially many. Strange stars exist at our knowledge boundary. We can theorize but not test, observe but not confirm, calculate but not solve. They remind us that knowledge has limits. that some things remain beyond current reach, but boundaries move. What's unknowable today might be obvious tomorrow. Strange stars might go from mystery to textbook in our lifetimes. The universe doesn't care about our curiosity. Strange stars, if they exist, have been around for billions of years. They'll continue for billions more. Our brief attempt to understand them is a blip in their existence. This cosmic patience is humbling but also liberating. We don't need to solve everything now. The mystery will wait. Future generations might succeed where we struggle. Despite all our knowledge, wonder persists. Strange stars amaze me as much now as when I first learned about them. More knowledge has brought more mystery, not less. This persistent wonder is precious. It drives science, inspires exploration, connects us to the cosmos. Strange stars gift us wonder whether they exist or not. Strange stars are hypothetical objects made of deconfined quarks, denser than neutron stars, possibly more stable than normal matter. They might form from massive star collapse, neutron star conversion, or primordial processes. If they exist, they challenge our understanding of matter, stability, and stellar evolution. We don't know if they exist. Observations are ambiguous. Theory is uncertain. Searches continue with improving technology. The mystery persists. You now possess deep knowledge of strange stars, their theoretical foundation in QCD, their possible properties and behaviors, the observational searches, the implications for physics, the philosophical challenges, the ongoing debates. This knowledge connects you to the frontier of astrophysics, to questions without answers, to possibilities that strain imagination. Knowing about strange stars changes how you see the night sky. Any star might be strange. Matter, atoms, might not be fundamental. Stability, everything might be metastable. Physics, we don't understand everything. Discovery, surprises await. This changed perspective is permanent. You can't unknow strange stars. The strange star mystery will be resolved, perhaps soon. Gravitational waves might reveal them. Laboratory experiments might create strange matter. Observations might identify them conclusively. Theory might prove them impossible. Whatever the answer, it will transform physics. Find peace in uncertainty. Strange stars might exist or not, but either answer is wonderful. If they exist, nature is stranger than we knew. If not, we'll understand why. Learning something deep about matter's limits. Sleep tonight, knowing the universe holds mysteries. Dream of quarks and density, of matter, pushed beyond limits. Wake tomorrow connected to questions that challenge physics itself. The strange stars wait in possibility. Their existence or absence matters. The search continues. The wonder persists. The mystery deepens. You are part of this search now, carrying wonder about matter's strangest possible form. Forever changed, forever wondering, forever connected to the strange possibility. Strange stars,